Okay, so today we're going to combine our lessons on mechanisms and catalysts, and we're going to bring it in and apply it to coordinate diagrams. So we're going to kind of start putting things together. We learned before that most reactions don't happen in just one step. So the coordinate diagrams we've drawn so far just show a one-step process. But in fact, every step would have its own coordinate diagram because every step has a certain amount of activation energy, and every step will have a certain enthalpy change as well. So we can combine all these things together. So we're going to be able to draw a coordinate diagram from a mechanism if we have all the steps, and we know kind of the changes in the enthalpy of those steps and the relative speeds of those steps. Remember that a large activation energy is a slow reaction. If you have to add lots of energy in to get something to go, it's a slower process. It takes more energy. The rate determining step will have your highest activation energy because it's the slowest step. And remember that fast steps will have really short little hills because they don't take much energy. They happen pretty quickly all on their own. If a reaction is exothermic, then we have to have our reactants with more energy than our products, so the products have lost energy. If it's endothermic, then our products have gained energy. They'll end up higher. So here's an example of a coordinate diagram for this mechanism. If you look at our first step, we know that this step is slow. That tells me that it has a high activation energy. And we know that this step is fast, so that means it has a lower activation energy. Now, they didn't tell me anything about the delta H for either of these, so we could make those up. But we know the whole reaction, the net reaction, is exo. So that means that the whole reaction from very start to very end must end lower than you started. So this is what a coordinate diagram may look like, given the information that we have. So what you should see is that step one has a high activation energy. Notice there's two hills here. This is kind of representing step one, and this is step two. And so the first section of the graph, we're looking at step one. It has a really big hill, a really high activation energy because it's the slow step. Now, they didn't tell me what the delta H was for that step, so we can just make it wherever we want. I just ended it higher, so we just ended it up here. So your delta H for that one would be positive. That step we would say is endo, the way it's drawn. We don't know. They didn't say, so we can draw it however we feel like. But the second step is the faster step, so it must have a lower activation energy. So that means that you see our hill here is lower. So I've shown that. And then the last thing from the information is that the whole reaction is exothermic. Okay, so here's where I started. To be exothermic, we have to end lower. So that's where our exothermic reaction happens. So I've satisfied all of the information there. Notice that it says the coordinate diagram may look like this. So based on the information I'm given, that's the best coordinate diagram I can draw, but it's showing, kind of relatively speaking, what's happening between steps. So notice step one has a much higher activation energy, and delta H is negative for the reaction. And that satisfies drawing that coordinate diagram. So we're going to draw another coordinate diagram. These are just sketches. They don't have to be anything fancy, but I'm going to draw a set of axes. And I'm going to break it up because there's three steps here. So this is going to be step one, step two, and step three. And what I'm going to do is I'm going to look at all the information they gave me, and I'm going to try to graph that out, represent it visually. So if we look at our steps, our fast steps has the lowest EA. Our medium step will have the medium EA, and our slowest step will have the biggest EA. Because the bigger the activation energy, the slower the reaction. Now, the exo and endothermic bit will tell me where I need to start and end each step. And then the last thing is we got to notice that the overall reaction is exo. So wherever I start my graph, I have to end below that. So I'll start my graph. I would just start somewhere in the middle. So there's my starting point for my reactants. My activation energy for this step is medium. So I'm just going to draw a medium-sized hill, whatever I feel like. So I'm going to call that a medium-sized hill. And because this reaction is exothermic, that means I have to end below where I started. So I'm going to bring this curve down and end there. Now if I look here, here's my EA. and here's my delta H. Now my next step is slow, and that means I have to have a higher activation energy than the first step. So I don't necessarily have to, like, because of where I'm ending or starting from, I don't necessarily have to go way up here, just as long as my distance from this point here to wherever my top of my hill is bigger than that distance. So I'm going to exaggerate it though. Just might as well, why not exaggerate the way this looks so that it's pretty obvious that this is the slowest step. So I'm going to make this nice and big. I didn't have to go that high, but we're going to do that anyways. And now this step is endothermic, so it has to end up higher than the beginning of the step. So I'm going to come down there, and that makes it higher than where I started. So if I do this, this is my activation energy of the second step. I'll call this EA1 and delta H1. And then this is my delta H of my second step. Now my third step is fast, so it needs to have a really small hill. So I'm going to draw just a little hill there. That looks like it'd be really fast. And then the the delta H has to be exo, and the whole reaction has to be exo. So I'm going to bring this down, and I've got to start, or I started here, I've got to end below that. So I'm going to end it way down here. So it'll look like this. So here's my delta, or my EA3 and my delta H3. And if you look at the whole thing, so if I bring this line all the way over, this would be the delta H of the net reaction. So notice my delta H has gone down. I've satisfied all the parts of that mechanism, all the information that I was given. Now, you can only draw what you're given, so if you're not given information, you get to make up where you start. Like if I don't give you enthalpy changes, you make up where you start and end. It's mostly about, relatively speaking, the size of the hills, where you start, where you end, that kind of thing. So the next thing we're going to talk about quickly is catalysts. And remember that catalysts speed up reactions without getting used up. You get them back. An example of a catalyst in real life or in our bodies is an enzyme. They're a catalyst to get things to break down, but we get those enzymes back. We talked about homogeneous or homogeneous catalysts because they're in the same phase as the reactants. We also have heterogeneous catalysts that are in different phases. We talked about a catalytic converter in cars before. But how do they actually work? Well, we said that they lower activation energy, but what does that look like? Well, they allow the reaction to proceed by a different mechanism, a new pathway. And that new pathway has a lower activation energy. So if we look at this coordinate diagram, a normal reaction would have that nice big hill, but the catalyzed reaction has a much shorter hill. It's got a shorter path. It's like giving the reaction a shortcut. But the key that I really want you to see is this, that your delta H is not changing. You still start and end where you still start and end in the same place. So the distance from start to end is not changing, but how you got there is. It's almost like if you relate it to physics, it's your displacement in physics. You could take whatever pathway you want to get from point A to point B, but your displacement is just the difference between those 2 points. And that's really what delta H is, the difference from start to finish. Well, how they work. So like I was saying earlier with the Maxwell-Boltzmann distribution, when you add a catalyst, you've shifted that activation energy. You've reduced the threshold for a reaction to go. So it's almost like instead of it being a 50% to get a credit in this course, it would be maybe like a 30%. It would make it a lot easier for people to pass the course and get their credit. So that's what you're doing. You would give basically more molecules a chance to escape or react or whatever. So remember, they don't change delta H. That's determined by the energy that's in the bonds that are being broken and formed. Some examples of catalysts, I said enzymes in your body, catalytic converters in cars, and then we've also seen we talked about chlorofluorocarbons in the atmosphere decomposing ozone into oxygen. And that's why they were so bad, because you keep getting them back. Remember that they're involved in the reaction, but they're not used up, and I keep saying that over again. But once that reaction's over, you get that catalyst back, and it's not consumed in the reaction.